All right, so now let's look at some toughening mechanisms for ceramics. All right, so here's three that we're going to talk about. Here's three toughening mechanisms we're going to talk about today. And so, what these toughening mechanisms do at their very basic is rely on increasing the energy it takes or needs to extend a crack. So, all of these mechanisms assume we have flaws. So we're not going about a method of trying to eliminate flaws at this point. What we're doing is saying we're sort of conceding the point that we have flaws, and we're going to try to increase the energy it takes to extend that crack. And so that's working with that capital GC term that we talked about, is increasing the energy it takes to extend that crack. And so there's some different strategies, and we're going to talk about three of them. So the first one is crack deflection. So we're going to try to deflect the crack as much as possible. The next type of mechanism we're going to talk about is crack bridging. And so this is where we effectively try to put things between the crack along the perpendicular to the crack tip, and these will increase the energy it takes to expand the crack. And then the third one that we're going to talk about, which is sort of a specific example in the ceramic system, is to deal with a phase transformation that basically counters the crack propagation. And so we're going to look at these three mechanisms today, but we'll start with the first two. All right, so before we go on, though, I've kind of given you a very basic sort of definition of each of these. So what I want you to do is see if you can come up with an example, at least one example of each of these types of mechanisms. I think everybody will probably have easy enough time with one of these, but maybe more difficult on the other two. So see if you can come up with some examples, pause the video, write them down in the questions section, and then we'll talk about some options for these mechanisms. All right, so let's look at the first one, crack deflection. And so fracture toughness, if we look at polycrystalline materials, we see that the values of fracture toughness for polycrystalline material are higher than a single crystal. So if we take alumina, for example, I've put the values from our textbook down here. So single crystal alumina has a fracture toughness, K1C, of 2.2 megapascal meters to 1/2. Whereas polycrystalline alumina is actually closer to 4, approximately 4 with the same units. And so this is all due to that crack deflection. So if we have a single crystal material, right, then we would be dealing with cleavage type fracture within the material. There's nothing to sort of deflect that crack propagation. But now let's say we have a polycrystalline material and there's a crack along the grain boundaries, right? So it starts over here. Well, if we want this crack to extend at this junction point, then it has to either go by an angle theta up or an angle theta down, right? To go around this grain, right? So every time it encounters a grain boundary junction, it has to make a decision and go by a certain angle, and that change in direction costs some energy. And so this is kind of a simple expression. Oops, sorry, let me go back. About the fracture toughness at the tip based on what is applied. Excuse me. And it's all related to this angle. So if we kind of assume an average angle of about 45, then that means that the fracture toughness is going to be 1.25 greater. So the more we can deflect it, basically, then the better that is, right? And so that's the principle here with polycrystalline versus single crystal. But that's just one example of this type of mechanism. Another mechanism would be, let's say we have a matrix ceramic, so just a bulk ceramic that we have, and then we put these rod-shaped particles in that matrix. So we're basically putting an additive into this material. So here's sort of our crack front, this line, this dashed line. So basically we're saying it starts over here, and then it wants to move along whatever crystallographic plane or grain boundary towards the right over here. Well, once it gets to this first rod-shaped particle, because of the sort of anisotropy, the aspect ratio here, when it gets to this, it either has to go through. So we're assuming here that these rod-shaped particles are tougher than the matrix material, and so it would cost more energy to go through. And so if it doesn't, it has to deflect around it, right? And since there's these rod-shaped particles that have this long aspect ratio, and so it takes a long path around each of these rod-shaped particles. So that's kind of the idea here, is that we have to increase the energy put into the system to go around all of these particles, and so that increases the fracture toughness. All right, so that kind of brings us naturally to the next method, which is crack bridging. There's actually a lot of connections between these two. So we talked about these rod-shaped particles. Well, let's say we have a very similar mechanism. So again, here is a schematic showing a crack tip. So this is basically a matrix material, and then this is the crack tip. Well, let's say we now have these fibers in the material, very long particles here, sort of along perpendicular to this crack tip. So in that case, when we expose this to mode 1, right, so we're basically trying to pull this and extend this crack apart, excuse me, it wants to open, there's the stress concentration here, and it wants to move towards the right. Well, now we have these rod-like particles or fibers in the way, and so when we apply a tensile force, that force is being distributed across these fibers as well. And so what we can model them as little springs. So imagine that these are springs. And so what happens is that as we pull them, they extend, right? So we're basically applying a tensile test to these fibers. And so if they're perfectly elastic materials, then they're going to extend up to a point in which they break, right? And so that elastic energy that goes into it then causes that elastic energy that has to go into the system makes it tougher, right? Because we have to put energy into extending these materials. And so we basically, what's happening here is that you can think of these fibers that bridge this crack as creating a sort of closure force or something that clamps down on the crack front. All right. So these fibers or ligaments can be in the form of whiskers, fibers, elongated grains, a number of different things here. And so the whole field of glass fiber, Kevlar, all those sort of composite materials really have to do with what we're talking about here with crack bridging. All right, so these, excuse me, so these ligaments, again, are elastic and create this closure force and kind of act as tiny springs, and that those springs consume energy, that elastic energy that goes into these materials. All right, so here's sort of the defining equation for composites with particularly related to crack bridging, and how we can use that to increase the toughness. So this is the K1C, so the toughness of this material, and it's related to a number of different factors here. So let me just sort of walk you through what this all means. So when you see the subscript C, like here, that refers to the composites property, so the entire composite, everything, every material. If you see M, it refers to the matrix. So what the fibers are added to. And then F is obviously for the reinforcement fibers. So then V refers to the volume fraction, R the radius of the bridging ligaments. Sigma F here is the strength of the reinforcement, and then these values here refer to the ratio of surface energy or fracture energy in these cases. And so what we see is that there's a number of ways that we can increase the toughness. So we can do it by increasing the amount of fibers we put in. So that's the volume fraction of fibers. We can increase it by increasing the fiber's modulus, so using a material that has a higher elastic modulus. And here's the last one. So this is the one that's kind of not as obvious, but we can actually increase the toughness if we weaken the interface between the fiber and the matrix. So the interface holding these two materials together. And so that would be sort of partially debonded in a case here. So that's one that doesn't necessarily make sense right off the bat. So we'll talk about this in a second here. All right. So let's say that we have this weak interface between the fiber and the matrix. So what that would do is it would lead to some partial debonding. So you can kind of see that illustrated here where this is pulling apart, right? And the reason this doesn't seem obvious, it seems like that would be a bad idea to have the fibers not completely intact. But if we think about it from a tensile test point of view, that does make sense. So let's take the case here where we have debonded. So then the part that's in the grip is extended. So basically the part that's being gripped or held by the matrix extends up here and down here instead of all the way to the crack tip. So what that does is it extends the gauge length, right? It makes the gauge length of our little tensile test here longer. So what that does is it means that more energy has to be put into the system because the length of the test specimen, the fiber, is longer because of this debonding. So that's why a weak interface is actually good in these cases, because we're basically increasing the gauge length and therefore increasing the amount of energy it takes to extend the crack. So another reason that this weakening can be good is because the energy it takes to sort of pull the fibers out. So fiber pull out when they rupture also still consumes energy. So the act of sort of debonding the material as well consumes energy. And so here's the kind of image, I believe this is an SEM image of fibers on a fracture surface that have been pulled out of the matrix, and therefore that would consume energy and toughen the resulting matrix.